So in this video, we'll be looking at the third colligative property. The third colligative property, which is going to be vapor pressure lowering. In the last two videos, we looked at boiling point elevation and freezing point depression. So if you missed that, be sure to check out those videos. But in any case, we'll be looking at vapor pressure lowering in this one. And so vapor pressure lowering is another colligative property, and that means it is one that is dependent on the number of solute particles, not the chemical identity of those particles. But let's look directly at the formula, because I think that will help us clearly see the relation between our amount of solute and our vapor pressure. So the formula that you would need to know here, or that we'll commonly be using, is going to be the pressure of our solution. The vapor pressure of our solution is going to be equal to the mole fraction of our solvent times the pressure of the solvent. And so this is the formula that we're looking at. And so something that may jump out at you is this X. What is this mole fraction? What does that mean? Well, your mole fraction is, as the name would suggest, the fraction of moles that your solvent makes up in a solution. So, of the total number of moles. So let's say that we have a solution, and the mole fraction would simply be the number of moles of our solvent divided by the total number of moles. So the total number of moles in the solution would be the number of moles of solvent plus, the number of moles of our solute. Together, solvent plus solute makes solution. And so the total number of moles of our solution is what we're dividing by the number of moles our solvent is. And that gives us our mole fraction. So let's say we were looking at a saltwater solution. In that case, well, our mole fraction of our solvent's mole fraction would simply be the number of moles of water divided by the total number of moles. So that's the number of moles of water plus the number of moles of salt. And so it's just from this relation directly, we can see that our mole fraction plays a direct role in what our vapor pressure would be. And so from this, well, we can see what effect changing the amount of solute would have, right? Let's say that we increased the number of moles of salt. Well, what would happen to our mole fraction, and what would be the result to our vapor pressure? Well, if we increase the amount of salt, we're increasing effectively the value of this denominator. And by increasing the value of the denominator, we are effectively decreasing the entire value of this fraction, right? If we had, let's say, 1/10, that is 0.1. But on the other hand, if we had 1 over 100, that gives us 0.01. By raising the value of our denominator, we decrease the value of our fraction. So in this way, we can see that by increasing our solute concentration, the number of moles of salt in this case, we are decreasing our mole fraction, which directly will be decreasing our vapor pressure. And so we can see that our vapor pressure here and our solute concentration, remember these square brackets imply concentration, they are inversely related. As we increase the amount of solute, as we increase salt in this case, we decrease our vapor pressure, and vice versa. So hopefully that makes some sense. And now before we move on, let me just kind of add in another fact here. This formula that we're working with right here actually is the one that is associated with what is called Raoult's, that's kind of a weird, Raoult's law. Raoult's law. And so when we hear Raoult's law, well, we're really referring to this formula here, or we're going to be using this formula for the most part for Raoult's law problems, where we'll be trying to find our vapor pressure, or in other cases, we may be given the vapor pressure and we need to find the mole fraction. Or we're given the mole fraction and the vapor pressure, and we need to find the pressure that the solvent normally exerts. But in any case, this is Raoult's law, and this is the formula vapor pressure lowering, that is a colligative property. And now let's just look at an example. Let's look at a case where we would use this formula. And like I've said in the previous videos, this is more of a proof of concepts just to demonstrate how this would work. I'm going to be making another video in the future where I go into more detail with a lot more problems relating to colligative properties, so be on the lookout for that. All right, so in this problem, we're told that we have 25 grams of NaCl that is dissolved in 400 milliliters of water at 25 degrees Celsius. What is the vapor pressure of the solution? And we're given that the vapor pressure of pure water is 23.8 torr at 25 degrees Celsius. And we have to assume that the density of water here is just 1 gram per milliliter. All right, and just be in mind, or be wary of the fact that vapor pressure is something that can change with temperature. So it is at 25 degrees Celsius. We're provided with the value in this case, so it's not a problem. But in any case, let's start by finding the number of moles of NaCl, the number of moles of water, right? Remember that Raoult's law formula that we were dealing with before is just the pressure solution. It's going to be the mole fraction of solvent times the pressure of our solvent. So, well, to find this mole fraction, we know that we need to find the number of moles of water and the number of moles of our solute, in this case NaCl. So let's start with that. Well, to find the moles of NaCl, we need to first have the molar mass of NaCl. And so again, this is a calculation that I did off screen. Trust me when I tell you that the molar mass of NaCl is going to be about 58.44 grams per mole. Again, if you wanted to do this yourself, you would simply add the molar mass of sodium and chlorine together. So now we know that we have 25 grams of NaCl. We have the molar mass, 58.44 grams of NaCl per 1 mole of NaCl. Well, canceling that out gives us an answer of 0.428 moles of NaCl. Alright, let's just keep that number in mind for a moment. I'm going to clear up some space. And so let's just write that over here. Our moles of NaCl is equal to 0.428. Well, now what about water? Well, we're told that we have 400 milliliters of water, and so we need to first go from this volume to a mass, and then we can use the molar mass of water in order to find our moles. Well, we're told that we have 400 milliliters. We know the density of water to be 1 gram per milliliter, so that's 1 gram per milliliter. Canceling out milliliters gives us 400 grams of water. And now, just trust me when I tell you, the molar mass of water is going to be about 18.02. So we can convert this 400 grams of H2O into our moles of H2O very easily like this. Canceling out our units of grams gives us an answer of 22.2 moles of H2O. All right, again, let's keep that number in mind. So our moles of H2O is 22.2. All right, now let's find that mole fraction of the solvent, right? The mole fraction of our solvent, which is water in this case, is simply going to be the moles of water, 22.2, divided by the total number of moles, which is 22.2 plus 0.428. This is 22.2 divided by 23.056, which is going to be equal to 0.9629. So this here is going to be our mole fraction for our solvent. All right. Now, well, finally, we can calculate the vapor pressure of our solution, right? How do we do this? Well, let's just, again, the mole fraction of our solvent is 0.9629. And well, according to this formula, the vapor pressure of the solution is simply going to be equal to 0.9629 times the pressure of our solvent, which is given to us in the problem. The vapor pressure of pure water, our solvent, is 23.8 torr. It is 23.8. Just make this an X. Torr. And so then our answer here is going to be equal to 22.9 torr. That here is going to be the vapor pressure of this solution. So the vapor pressure of this NaCl solution at 25 degrees Celsius is about 22.9 torr, slightly lower than that of pure water. So we can see that this colligative property holds true, right? The vapor pressure does decrease. And so this again happens because the solute particles are sort of trapping our solvent molecules in the liquid phase, preventing them from escaping into the vapor phase, which is kind of the core idea here behind vapor pressure lowering. So anyway, hopefully that made some sense and you found, some value out of this video. If you did, please show your support by liking and subscribing, and leave in the comments what you'd like to see next. And keep an eye out for the next video on colligative properties, where we'll be looking at osmotic pressure. But in any case, I'll see you guys in the next video.